Welcome to EE 5110 Probability Foundations for Electrical Engineers. In this lecture, we will look at the concept of random variable and how we can characterize a random variable using probability distribution function. More specifically, we will use three different functional characterization. One is called as the cumulative distribution function, and another the probability density function, which applies for continuous valued random variable, and the third is the probability mass function, which applies for the discrete valued random variable. So to recall, a random variable is a function that maps the events from the event space or the sigma algebra defined on the sample space of the random experiment to the real axis. So it is a real valued function with its domain as the sigma algebra and its range as intervals or points in the real axis. So the definition goes as follows: random variable, if you denote the random variable as x, okay, and the notation x dot means dot can be any event belonging to the event space, okay, x is just a function and the domain is the entire sample space, and the range is a subset of the real line. For example, consider an event EB, event in the event space which has to be a subset of the sample space. Then x maps this event to an interval in the real axis. We saw that the event space forms a sigma algebra, which means that the class of all events are closed under finite number of set complementation operation, set union operation, and therefore the set intersection operation. We also saw that the entire sample space and therefore the empty set or the impossible event should also be present in the sigma algebra. So which means that if you map events onto intervals on the real axis, these intervals should also obey these properties. That is, if an interval is a mapping from an event, then the complementation of the event will correspond to the real axis not containing the interval. Similarly, unions of two events will translate to union of the intervals on the real axis, and so on. So which means that the random variable induces another sigma algebra on the real axis, which takes a special name called as the Borel field. So Borel field is nothing but a collection of intervals on the real axis which obey the property that if these intervals are themselves closed under the complementation operation and the union operation. Here these intervals are subsets of the real axis. Then we will move on to the another important property or one condition that we enforce on the Borel field. The thing is, it's not just that the intervals on the real axis to be closed under set complementation and the set union operations on the real axis. We also enforce that intervals of special kind to be present in the Borel field. That is, all intervals of the form, okay, minus infinity to x should be present in the Borel field. So this is a condition that is necessary to construct a Borel field. So which means that if you look at events of this type, that is a set of all sample points such that x of psi, okay, less than or equal to x, means that this corresponds to all events such that the value taken by all sample points in the event should take value less than or equal to a given value x. Okay, so such events should be present in the event space, and this corresponds to an interval in the real axis, which can be compactly written as random variable capital X less than or equal to a value small x. So these events are of unique importance, and we expect that we should be able to assign probability measures to such events, and these events are what we call as the probability distribution functions. So all such specification of probabilities to intervals of this kind, x, that is the random variable x, less than or equal to, taking value less than or equal to a given value small x for every value x in the real axis. All such probability measures should be present, should be definable. We should be able to define them. So this is a requirement. The reason why is all sets of engineering interest. If you are interested in assigning probabilities to events that is of interest to engineers as well as scientists, okay, those events can always be constructed using events of the type minus infinity to x. So that is the reason why we are interested in these kinds of intervals. So we saw that events mapping to these intervals on the real axis, okay, have a one-to-one correspondence. So henceforth, for a shorthand notation, we can even call these intervals on the real axis as events themselves. So the events on the sample space which map to these intervals can be called such that these event corresponds to the case where the random variable takes a value less than or equal to a given value small x. So we will use this shorthand notation. Henceforth, we will call these intervals on the real axis themselves as events, but these are nothing but intervals mapping on, or which are the maps from the events in the sigma algebra. Now, having defined these intervals which is of prime importance to us, and the probability measures are assigned for these intervals as what we call as the probability distribution function, we will define it now formally. So a probability distribution function denoted as PDF and represented in notational form as capital F subscript of capital F subscript of capital X, and within bracket the value small x, okay, is defined as f. We will call it as fx of x. So in this context, the f means capital F and x is the random variable and it is denoted as capital X, and this is the small x denoting the value taken by the random variable capital X. So this is nothing but the probability measures of all such sample points such that the value corresponding to the sample point, which is the mapping defined by the random variable, are of such a nature that those values are less than or equal to a given value small x. So this event is analogous to this interval. So we will call this itself as the event. So the other way of specifying the PDF, probability distribution function, is the probability measure of the event minus infinity to small x, okay, and this x indicate that we are talking about the random variable capital X, okay. Sometime we will use the notation, okay, cumulative distribution function in place of the probability distribution function, so that it becomes clear that we only talk about the probability which is a cumulative one starting all the way from minus infinity to a given value small x. So we see that under the mapping defined by the random variable x, we have generated a new probability space. We originally had the probability space sigma, and then the event space, and then the probability measure on that one, the probability triple we had. Now we have an equivalent probability space where in place of the sample space sigma, we have the entire real axis R, and in place of the event space, which is a sigma algebra on the sample space, we have the Borel field, which is intervals in the real axis which are complete under the complementation and union of intervals in the real axis, which includes the additional constraint that the entire real axis should be present in this one, and the interval, okay, of size 0 should also be present. So these two, on this Borel field we have a measure being defined, and that is the probability measure of the random variable x. So henceforth we will work with this probability space, okay, and we will only be talking in terms of the random variables and the probability triple R, B and Px. So R is the real line, B is the Borel sigma algebra of all subsets of R, which are generated by countable unions and intersections of sets of the form minus infinity to x. We will see that if we have all sets of this form, then all events of interest to us, okay, will map to intervals, okay, whose probability measure is what we are interested in. So Px is a set function assigning number Px of A, which is has to be greater than 0 for all set A, which are elements of this Borel field. Now, if we look at the properties of this probability distribution function or the cumulative distribution function, we see that these properties automatically follow. 1. Fx of infinity means we are talking about probability measure of the event corresponding to the interval minus infinity to plus infinity. Since this is the entire real axis and the sample space has to map to a subset of the real axis or at most the entire real axis, so the corresponding probability measure, okay, is nothing but the probability measure of the entire sample space, and therefore that is equal to 1. Similarly, if you evaluate the quantity fx of minus infinity, this corresponds to the interval minus infinity to minus infinity, which is an interval of 0 range, and therefore it corresponds to the impossible event for whose probability we have already assigned as 0. So fx of minus infinity is equal to 0. Then we can also see other properties. Fx of x is a non-decreasing function of x. What it means is, for two values x1 and x2, such that x1 is less than or equal to x2, then fx of x1 has to be less than or equal to fx of s2. We will elaborate this point soon, but it can be seen that this corresponds to the interval minus infinity to x1, whereas this corresponds to the interval minus infinity to x2, since x1 is less than or equal to x2, this interval minus infinity to x1 is a subset of the interval minus infinity to x2, or this is contained in this one, and therefore the corresponding events in the sample space, if you call it as A and B, the event A is a subset of event B, and therefore the probability measure of A, that is P of A, has to be less than or equal to probability measure of B, and that is why we have this relationship coming up. Then, since fx of x is defined to be probability that the random variable x is less than or equal to x, okay, it can be seen that fx of s is continuous from the right, okay, because the equality sign is there apart from the less than condition. It has to be continuous from the right. More technically, fx of x can be nothing but in the limit epsilon tends to 0, fx of x plus epsilon, okay. So next we will move on to looking at what is the implication of these properties. Okay, first let us look at an interval of the form capital X, the random variable, taking value between two given values x1 and x2, such that it is x is small x1 less than x less than or equal to x2. So here it is equal to where it is less than, that is to be noted, for x2 being greater than x1. Okay, then if you assume that this interval is a non-empty one and it is an element of the Borel field, okay, and if this condition is met, then it will be strictly non-empty, then we will see that the probability measure of events of this form should lie between 0 and 1. Okay, how? We know that x less than or equal to x2, this interval, this set, can be written as the union of two disjoints. One x less than or equal to x1, another x between x1 and x2. Okay, so we can see that we know that if the corresponding events, if you look at, we have one event A, which is a union of two events B union C, and B intersection C is equal to null set. These probabilities add up, and these probability measures of these intervals are what we call as the CDF or PDF. Therefore, this is nothing but if you take the probability measure on this one, the union becomes, these are all events, and once you take the probability measure, then this becomes plus. So this is nothing but, after taking the probability measure, this is fx of x2, this would be fx of x1, and that is nothing but the probability measure of the random variable taking values between x1 and x2. And on rewriting, we get that the probability measure of the random variable taking value between any given interval in the real axis can always be found out from the CDF by applying this formula. This is why CDF is of utmost importance to us, because all events that is of interest to us can be represented as a random variable taking values in some finite interval in the real axis that can always be found out by manipulating the CDF in this form. Going beyond, then suppose the probability distribution function CDF is continuous and differentiable. Then we can define another function, what we call it as the probability density function, as follows. Again, for the probability density function, we use the small f as the symbolic notation for that. Okay, so that is read as small f of capital X of the value x is nothing but the d by dx of the CDF or the probability distribution function fx of x. This is defined only when or only over the interval where fx of x is continuous and differentiable. At those points where there is a discontinuity, we cannot define the density function. Okay, so the point that we have to note here before I proceed further is that for all random variables we reserve the capital the symbols, okay, which are the uppercase symbols. So we have to denote the random variables only by uppercase symbols like capital X, capital Y, capital A, B, Z, or P, Q, and so on. And the value taken by these random variables are denoted by the corresponding lowercase symbols. Okay, so if you call it as small x, it generally means, although it is a dummy variable, it generally means the value taken by the random variable denoted by the corresponding uppercase symbol, that is capital X. Well, now if you look at the properties of this probability density function, again we may use the shorthand notation PDF for this. So here, which is written like this one, here there can be a confusion whether if you use the acronym PDF, does it denote probability density function or the probability distribution function. So mostly in this course I will reserve the term cumulative distribution function to denote the capital Fx of x, and the probability density function to denote for this function of this type. We will rarely use the term probability distribution to avoid any such confusions. So we can see that small fx probability density function small fx of x has to be greater than or equal to 0. That simply follows because we saw that the CDF is a non-decreasing function. So it may increase or it may remain at the same value, but it can never decrease as we go along the x-axis in the positive direction. So which means that when it remains constant, the value of the density function becomes 0. Whenever it increases or then it is positive and it can never be negative. Then if you perform an integration of fx of x, okay, over the entire real axis, that is minus infinity to plus infinity fx of xi d xi, okay, then we can then apply the end conditions. It becomes the CDF evaluated at plus infinity minus the CDF evaluated at minus infinity. We have already seen that this corresponds to the probability measure of the entire sample space, which is 1. This corresponds to the probability measure of the null set, empty set, or the impossible event, which is 0, and therefore this is equal to 1, which means that the density function is normalized. That is, the integral of the density function over the entire real axis should always evaluate to 1. Well, a small note, since we have reserved the symbol xi to denote for sample point, we generally, this is not a very good way of denoting. It should have been better if you have used the symbol y instead of xi as the dummy variable of the integration. Next, we can recover the CDF from the PDF by integrating the PDF all the way from minus infinity to the place where the CDF is evaluated. That is, fx of x can always be obtained by integrating from minus infinity to x fx of y dy or fx of xi dz. Okay, so because this will evaluate to this the probability measure of this interval, which is what the defining value of this CDF. More importantly, we will see that if you find the difference of the CDF at 2 points x2 and x1, for x2 greater than or equal to x1, then we can find that this can be written in this manner. Fx of x2 is nothing but minus infinity to x2 fx of xi dxi minus fx of x1 is minus infinity to x1, this one. So we can remove the interval, okay, minus infinity to x2, okay, subtract it out, and we will get only the remaining interval as x1 to x2 fx of xi dxi, which is nothing but the probability measure of the random variable x taking the value between x1 and x2. So this is another interesting and important property of the density function. Then we can generally we use the term density function to conveniently handle continuous valued random variable, because in which case the probability measure exists over an entire range, and therefore the probability CDF will be an function which is monotonic and increasing over the range where the measure exists. Okay, but in the case of discrete valued random variable, the random variable x, okay, takes values only at finite or countably infinite values in the real axis. So in which case we can see that the probability distribution function, or specifically the CDF, will be a staircase type function. And in this case the probability measure at all those points where they are defined, they are together called as the probability mass functions. Okay, because here the probability measures are lumped at only certain points on the real axis. Okay, they are similar to points where the masses are concentrated. So the PMF, or probability mass function, of a discrete valued random variable x is generally denoted using this symbol P capital X of small x, not fx of x, but px of x is the conventional way of writing it. So that is defined as the probability that x equal to x, that is the random variable takes the value small x, and indeed that can also be retrieved from the density function, but first writing it like this one. Px of x can be written as probability that x is less than or equal to x minus probability that x is less than x. Okay, so this way we can write it. And we can also note that Px of x is equal to 0 at all values where, okay, f of x is continuous and has a finite value, that is it continuous and it is non-increasing. So wherever the CDF is non-increasing, that is at these points, okay, then the probability measure is 0. Only where this CDF has discontinuities at these points, then the PMF exists. So Px of xi can be written using the CDF as fx of xi minus fx of xi minus, because this includes the interval from minus infinity up to and including xi, where this does not include xi. So if you subtract it out, we will have probability measure present at xi, which is what is the probability mass function at xi is. So we can see that this is nothing but probability x is less than or equal to x, less than x. Okay, then it's also possible that we can handle probability density, we can use probability density function notation even for discrete random variable, provided we define it properly. So fx of x is discontinuous at in the case of the discrete valued random variable, so the density function strictly speaking doesn't exist. But it is possible to define it using special functions such as the Dirac delta functions. How? What we do is we first define the CDF of a discrete valued random variable fx of s as sigma of many unit step functions with appropriate weightage. First, what are unit step function? Let us say u of y is a unit step function. It takes a value 0 for y less than 0 and 1 for y greater than or equal to 0. So at y is equal to 0, it increases by to a value 1. So these are all shifted step function. Okay, so they start taking a value from 0 to 1 at these points xi. So what we do is, for such unit step function, we give a weightage equal to the probability mass function evaluated at xi, and if you add all those unit step function, then we will end up getting the staircase function fx of x. We can easily see that this staircase function can be constructed by taking one unit step function which starts at this point and it takes a value up to infinity like this one. Then you have another unit step function, it takes a value like this one. But if you add these two functions, you will get a function which goes like this. And then we superimpose another unit step function and add it with these two and so on. Now formally we can differentiate this function. If you differentiate this function, we get the probability mass function for the discrete valued random variable, and that is nothing but these are just constants and we have to differentiate these functions. Unit step function on differentiation lead to the Dirac delta function of this form. So formally we can write a density function for a discrete valued random variable in this manner. But generally we will work only with the mass function. But when we have mixed type random variables which take value on a continuous range as well as at some specific point, it is better to use a unified function which is the density function and use this representation in a convenient manner. Okay, so what we will do is we will stop at this point. We have looked at how a random variable can be characterized using the cumulative distribution function, probability density function and the probability mass function. Then we will look at some examples of discrete valued random variable in the next lecture. Thank you.